All right, good afternoon and welcome everyone. My name is Abdullah, and today we have a talk on how Spotify uses Ray on Google Kubernetes Engine to run distributed LLM training. I will be presenting with Brandon from Google Cloud, and we'll be talking about GKE and how Spotify leverages it for distributed training. So over to you, Brandon.
Excellent. Thank you, Abdullah. And thank you, everyone, for being here. So as Abdullah mentioned, my name is Brandon Royal. I am a product manager on the GKE team focused on AI/ML workloads. So really pleased to be here with the Spotify team, sharing some insights around building large distributed platforms using Ray and Google Kubernetes Engine together. So we will sort of focus on two areas. So we'll talk a little bit sort of in general terms first, addressing some of the core challenges in distributed AI infrastructure. And what the Google Kubernetes Engine team is specifically doing, investments that we're making in order to solve some of those challenges. And then I'm going to pass it back over to Abdullah here shortly. He's going to show the really exciting stuff, which is how real customers like Spotify are implementing a lot of these features and capabilities in order to serve the needs of their ML users internally. So this is probably familiar to a lot of you folks. Has anyone ever run out of a GPU? Yes, okay. Has anyone had an out-of-memory issue with the GPU? Yes, right? So a lot of like consistent challenges, right? And Abdullah will talk about some of those challenges that they've seen on the Spotify side. But we know GPU scarcity is a perpetual, unfortunately, a bit of an evergreen problem within our customer base. And we know that a lot of these large-scale distributed distributed models, they require hundreds, thousands, tens of thousands of GPUs in some very large cases, and ultimately we need to efficiently orchestrate workloads across all of those. And then we also recognize that, unfortunately or fortunately, depending on which side you're on, NVIDIA GPUs and accelerators are quite expensive. So we need to make sure that we are getting every penny out of those accelerators to deliver value ultimately to you. So these are sort of challenges that we've seen across the board. There are many others. And we really believe that Kubernetes and Ray, it's a sort of a match made in heaven. It's really the perfect relationship to help address some of those challenges, both in terms of all the things you've heard through the course of the last couple of days around what Ray is doing, but also because, well, Kubernetes is about 10 years old, a little more than 10 years old, and is quite mature when it comes to large-scale orchestration of complex and stateful workloads. So it really is the perfect fit. So as the Kubernetes team, our job is to really sort of make that relationship work and make that relationship sort of last and serve the needs of our customers. And so one of the ways in which we're primarily doing that is to integrate features of KubeRay directly into Google Kubernetes Engine. And so these are optimizations, both in sort of the upstream KubeRay project, and I'm joined by some of my engineers, my colleagues that are doing a lot of upstream work directly in KubeRay, but also sort of bringing the KubeRay operational experience to the Kubernetes cluster and control plane. So with Ray on Google Kubernetes Engine, we introduced a new add-on a couple of months ago. And essentially, with one configuration, you can get the KubeRay operator deployed directly into your cluster. And that provides some sort of nice low-hanging fruit benefits, things like monitoring and logging and observability, additional scalability, additional security. So this is just sort of easy, nice-to-have things that we're adding on top of the great work that's already happening within the open source community. But sort of in broader terms, right, that's sort of the easy stuff, right? That's the low-hanging fruit just to make Ray easier to use within Kubernetes. The challenges that we're trying to address are sort of bigger challenges, especially when you think about large-scale ML distributed compute. We care a lot about helping customers to solve scale and performance. And that means improving cluster scaling in terms of horizontal workload scaling and node scaling, but also helping with price performance for both distributed training as well as for inference. On the obtainability side, we recognize this is a big challenge, right? And so this is an area that we're investing quite heavily across Google Cloud to help with this obtainability challenge. We recognize that not every organization can go and get a large reservation, sort of pay for all of their GPUs in advance for a full year. They need some level of dynamic allocation of those GPU resources. And so it's our job on the Kubernetes side and the Kubernetes Engine team to make that interface work. So as you're building your Ray cluster, or you're expanding your array cluster, how do you ensure that those dynamic resources that are allocated via GCP are made available to those jobs? So we want to make it easy for job execution. We want to make it easy for those Ray APIs, Kubernetes APIs, to express the needs of those resources. And then the last is densification. So in a lot of cases, some cases you might have sort of dynamic allocation of resources where you want GPUs when you need them, and when you don't need them anymore, you want to spend them down. But in other cases, you want to densify your workloads in such a way that you are maximizing the utilization of your GPU resources across the board. And we have some methodologies that we use internally we'll talk a little bit about, but in general, we're talking about sort of bin packing for Ray jobs and Ray clusters within your cluster and making that as easy as possible. And so one of the patterns that you'll hear from Abdullah is this sort of idea of ephemeral clusters and ephemeral Ray jobs, and that's one of the ways in which we can start to do that, combined with queuing and prioritization. So as a distributed platform, of course, like our job on the Kubernetes side is to make the infrastructure easy and to make it highly scalable, highly performant. And so there's a lot of things that we're doing in general to sort of make that ML experience great for our customers. And so you may be familiar, obviously you're familiar with GPUs, but we're doing a whole lot of work, of course, with TPUs as well. And so Ray is natively integrated into TPUs. It's been supported for some time. And so that gives you the flexibility. If you want to use GPUs, you can also use now TPUs, especially if you use frameworks like JAX. On the networking side, we heard a lot about sort of nickel yesterday. It's been a long week. And so we want to make that GPU to GPU high bandwidth, low latency performance as good as possible, right? And so we've made some specific investments in the latest generation of H100s to significantly improve that latency and performance. And then, of course, we're doing things on the storage side as well. And so we won't talk a lot about that stuff, but I'll just kind of give you a high-level view. These are things that we care deeply about. And really, it's just based on your needs as customers to sort of provide the best solution for that. Now, on the scaling front, we mentioned this sort of challenge of horizontal scaling, and how do we ultimately solve this? We now have base images within Ray, within PyTorch, anything basically with a CUDA library that's going to be tens of gigabytes. And so if those of you who are familiar with OCI images and sort of how layers work, this whole system of shipping around containers really wasn't designed for tens of gigabytes. And so the system actually ends up being incredibly slow. We've done some things recently in the last couple of years, things like image streaming, so you can sort of lazy load those layers together, but still you're sort of bound by the laws of physics. We have to move bits around from one node to another. And so one of the ways in which we're trying to solve that to increase the performance of cold starts is what we call secondary boot disk or container image preloading. So you can imagine a scenario where if you have a standard set of base images that you're using across your Ray clusters, you would essentially pre-bake those into your node pool. So every time a new node stands up, that node pool is essentially pre-provisioned, or that image essentially is pre-provisioned in a known location. So container D can go and basically pull it directly from the cache. So it significantly reduces the overhead of cold starts. And we've seen great examples of customers who have seen upwards of 29x improvements in startup performance with things like 15 to 20 gigabyte or 16 gigabyte container images. So that's one way in which we're helping to sort of improve performance, and we've seen that pretty consistently across a number of talks this week. But another way is on the data side. And so one of the ways in which Kubernetes generally expresses connectivity to backend data storage systems is via a CSI driver. And so you can consume a bunch of different storage backends. One of the ways in which sort of in talking to our customers, we see a data centricity around GCS or sort of object-based storage. So we want to make it as easy as possible for data scientists who are used to using object-based storage to consume that data within their GKE cluster and do it in such a way that they got optimal performance, both in terms of caching and parallelism. And so we've introduced what's called GCS Fuse, or Google Cloud Storage Fuse. And essentially what that does is it fuses sort of object storage into a file-like storage semantic. And that gives you significant performance improvements in things like parallelism and caching. So you can actually utilize those local SSDs that are sort of inherent in a lot of our GPU deployments. You've got these GPUs with very underutilized local SSDs. So we're taking advantage of those local SSDs by pre-caching that information. And we've seen, or that data, and that we've seen significant improvements in that. If you have multi-epoch training runs as an example, we're sort of caching that so the secondary and 2 to n epochs are going to be significantly more performant than the previous. On the obtainability side, so one challenge, again, we've seen is I want this GPU, I want it now, and I get a stockout error, right? And we monitor that, by the way. And so we realize this is a pain point that our customers experience. They tell us about it, unfortunately, just about every day. So this is the idea of GPU scarcity, unfortunately, is not going away. But really what we want to do is provide sort of better APIs and better experiences so we can help optimize GPUs for your use case. Essentially, make them available as soon as they're available directly to you. And there's a couple ways in which we are doing that. One is what's called a compute class. So there's actually a new paradigm within Kubernetes. So you can start to express priorities. So my highest priority is going to be whatever, an H100 with a spot instance. If that's not available, use my reservation. If that's not available, use this. Right? And we're continuing to extend this across single region, multi-region kind of use case. So this is one semantic that is being built into GKE and into Kubernetes to help with some of this problem. So we'll sort of prioritize if it's not available. We'll move down to the next one, so on and so forth. Another important semantic that we'll talk about is sort of queuing and this idea of, well, I want to put something in a queue, and as soon as resources are available, I want to execute against that. And the mechanism that we're using in order to queue is a project that we call Queue. We're really good at names. But this is actually an upstream Kubernetes project. And so this is actually a Kubernetes-centric queuing system. So it's Kubernetes native in that it uses Kubernetes-based objects. But it adds this sort of idea of on the specific cluster, you can specify a local queue and a cluster level queue, and you can provide sort of governance and control and prioritization around how those jobs are executed against that queue. And that's relevant in this case because now we want to start to queue up those ephemeral jobs, those ephemeral array clusters, and ensure that they're sort of bin packed, if you will, on the cluster itself. So for that densification problem that I was talking about earlier, as customers move more and more to ephemeral deployments of Ray jobs and Ray clusters, they can now start to take advantage of that queuing. So as soon as a resource pool is available for execution against that particular job, it can be then scheduled and executed. And we can see sort of the densification, a very sort of crude and simple example of how we can start to share resources across teams and introduce additional fungibility for resource allocation. Now back to the challenge of obtainability. We know that, again, the prioritization semantic doesn't work for everyone. That's a great semantic that might work in some cases, but in other cases you might want to say, I want a certain resource at a certain time, and I want it so up to a certain number of days. So I want n number of H100s available for 7 days as soon as they're available. And the way in which we're doing that is what's called dynamic workload scheduling. And again, this is a Kubernetes API that we're exposing actually across GCP. And this really allows you to say, again, I'm going to request the resources that I need. And with Queue, the project I was mentioning a second ago, we can now then dynamically schedule those resources as soon as those resources are available, or schedule the job, I should say, as soon as those resources are available. And you can do that in what's called flex mode. So as soon as they're available, I'm just going to schedule it, which we can basically take, we can deploy them in minutes and hours in some cases. Or you can also do it in what's called calendar mode. So in some cases, you have a specific training run, you want it to start at a specific time, and you can leverage it that way as well. So hopefully that gives you a little bit of a preview as far as some of the things that we're doing on the product side to help the Kubernetes project and help our customers with building out distributed ML platforms. I'm going to hand it over to Abdullah to talk a little bit about how Spotify has taken the approach of building out platforms.
Thank you, Brandon. So, my name is Abdullah. I am a machine learning engineer at Spotify. And today we'll be talking about, as customers of GKE, we'll be talking about how Spotify built its platform using the offering from GKE and some of the features that Brandon talked about, how we're currently using them at Spotify. So just a quick overview of Spotify's machine learning platform. We call our machine learning platform Hendrix, which essentially aims to facilitate an ML practitioner through every stage that they go through during a machine learning dev lifecycle. So from features to workflows to providing compute and model serving solutions. What we will be focusing on today is the compute layer. That's really our solution, which is built on GKE, and that's how we allow our users to provision or create Ray clusters and submit Ray jobs. And that's where we use a lot of offerings from GKE. Moving on, and just for a few minutes, I'll be giving some context so we understand how the platform works. So when it comes to the compute layer, and when it comes to a user trying to create a Ray cluster, if you guys remember the keynote from yesterday, Robert talked about complexity. Complexity is the enemy. So we do understand a lot of the stuff that actually happens on the infrastructure level is too low level. And that's not something that if you're a research scientist or an ML practitioner that you would want to spend too much time thinking about. Our solution to that is what we call Hendrix config layer. It is our abstraction over the low-level constructs that we deal with at the infra level. So as an example, when it comes to a Ray cluster, KubeRay recognizes a custom resource called Ray cluster, which is a YAML file. What we instead allow our users to is to keep and maintain a set of YAML files, which are an abstraction over the actual Ray cluster object. And so they can go in as much detail as they want to, but that's a nice abstraction, something that if a regular user who doesn't need to think about too much granularity can interact with and build Ray clusters. So they submit a YAML file. We take care of building a Ray cluster custom resource, applying the features that we leverage from GKE, and creating a Ray cluster accordingly. Moving on, again, very quickly, high-level overview of the user-facing side of machine learning platform at Spotify, which you can see on the left in green, and on the right is our infrastructure that we maintain on GKE. So we have stuff like, you can see Q, which I'll be talking about in a while. You can see a lot of stuff that actually happens on the infrastructure level, but we aim to provide good abstractions to our users and try to bring down the complexity. All right, so now to the problem. What exactly are we trying to address? And something that we actually saw when teams started using or showing interest in Gen AI use cases was mostly around GPUs. So a lot of times, you're trying to run a program, but the GPU that you have access to is not something that is fulfilling the compute requirements. So we actually had to rethink the GPUs we have and how do we optimize the GPUs so we're not wasting anything. Sometimes you may have a GPU, but it's not a GPU that actually fulfills your need. So training time could take long. A lot of problems, and based on that, if you do go to a bigger GPU, that also comes with a huge cost. So as a platform team, we also had to think about how can we have access to expensive GPUs, at the same time make sure that they're utilized well, and they're not sitting idle, we're not wasting money on the GPUs. And so the problem at hand really is the low utilization and over-provisioning of GPUs. So we want our teams, we want our tenants to use GPUs in a way that everyone gets a fair share, and the GPUs that we actually have access to are not being underutilized. And that's something that's a problem we will talk about, and we will be focusing on three key aspects that we leverage from GKE to resolve that problem. Network optimizations, storage optimizations, and scheduling optimizations. Again, quick context, the machines we use from GKE are A3 high. You can see the specs. You can also go to the GCP documentation, read more on it. But just to give you context on what Spotify uses currently, we are on A3 high, but in future, there is a possibility that we would consider using A3 mega. And so to talk about the features that we leverage from GKE to resolve the issue that I was talking about earlier, so GKE comes with high bandwidth interconnect that has been very useful at Spotify. So again, talking about the concepts, there's internode versus intranode communication. So usually for the workloads which require distributed GPU training, where multiple GPUs need to be in sync, need to share data, it's really essential that the network on which they're sharing data and they're communicating is one, fast, and two, reliable. And so GKE's offering has been really helpful. You can see the specs. When it comes to intranode, it's 1,000 gigabits per second. And when it comes to intranode, it's 200 per NIC, 200 gigabytes per second per NIC. So 4 NICs, that's 800, altogether 1,000 gigabyte per second. So the point being that the communication protocol or the networking that we use from GKE has been really helpful in making sure that the network is quick. GPUs that need to sync together are communicating reliably and quickly. So we make sure that there's no workload that is incomplete, or there's no bottleneck. There's no GPU that is sitting, or to make sure that we're actually utilizing GPUs to the best of their capacity. Another optimization, another feature that we leverage from GKE is the NCCL Fast Socket. So really, essentially, it's NCCL being NVIDIA's collective communication library, and it really also it's a transport layer plugin to improve NCCL collective communication performance on Google Cloud. What you can see on the right is a quick snippet. So I would keep making this point repeatedly, which is complexity is the enemy. So on the right, you can see a quick Terraform snippet, which is essentially how we leverage NCCL Fast Socket on GKE. It's really just 2 lines for our node pools. A user doesn't have to think about it. As long as it's enabled and available on GKE, a user can simply create a cluster using our config layer, and this is enabled for them. Again, in workloads that require distributed training, distributed fine-tuning, it has been a key to really optimize the network and make sure that the network is fast and is reliable. And with A3 High, we also have the ability to leverage compact placement from GKE, which essentially it makes sure that the nodes, the VMs that we're using, VMs with GPUs, are physically placed closer to each other. And so this can help in performance and also reducing the network latency among the VMs that need to communicate with each other. Similar idea you can see on the right is quick Terraform snippet. Again, this is something that we have to do as a platform team. And as long as we're leveraging it from GKE, a user doesn't have to go into too much details, and they can simply create a cluster and have access to the features that we leverage from GKE. Moving on, so the first 3 features we talked about were on the network optimizations that we're leveraging from GKE. We also do use features that are targeted on the storage optimization. And one of them, as Brandon also pointed out earlier, is GCS Fuse. So really in use cases where someone is fine-tuning distributed fine-tuning, a large language model, we often see a case where a workload is running for a long time, but for some reason the rate cluster goes down, and then the GPU power that you used for fine-tuning or for that job goes to waste. So we really needed a solution to persist or to checkpoint, to allow users to checkpoint their models. So if a rate cluster goes down, it can pick up from where it got interrupted. And so GCS Fuse has been a great solution. It allows rate clusters to access a GCS bucket as a local storage, local file system. And we have teams that use it to do model checkpointing, sometimes even to store data that is not directly related to checkpointing, but it helps in cases where there's long-running rate clusters that need access to, or long-running jobs that need access to some data. So just to make sure that if there's some compute that is spent on that job, it doesn't go to waste. And this storage optimization has been pretty tremendous in our use case. This is to show how, again, as a user, the config layer that we provide. Again, a lot of stuff goes on under the hood for the infrastructure, but if you're a user using it, all you have to deal with is simply a config file and enabling GCS Fuse in it. So if you're a user and you provide it in your config file, on the Hendrix side, on our platform side, we would take care of creating a rate cluster that has access to a GCS bucket, and it can treat it as a local file system. And finally, so we talked about 2 optimizations so far. We talked about network optimization, and we talked about storage optimization from GKE. The final optimization that we'll be talking about today is the scheduling optimization. So Brandon talked about workload densing problem and also GPU provisioning with DWS and Q. So really the problem that we ran into is Spotify had limited access to GPUs, but a lot more teams trying to use it. So with limited GPUs, you sometimes have teams fighting over those resources. So as a platform team, really had to make sure or understand what can we do to, one, ensure fair share usage, two, understand the priority of different jobs being submitted, and also make sure that no team is able to hold onto resources without using them. Our solution to this problem was to use Q and DWS. So just to show you a quick rundown on how it works at Spotify is a user begins with, again, simply there's a YAML file that corresponds to a job, and in the job, if they want to enable queued provisioning, which is our term or the term we use to really indicate that a job should be executed when the resources required by it are available. So a user enables queued provisioning if they want to use it by setting that option to true, submit the YAML file, and on the Hendrix side, what we do is we create a Ray job, which, again, another construct, another custom resource at the KubeRay level, and we submit it to our GKE cluster in the user namespace. Now, there's a local queue in the user namespace where team members sharing that namespace could submit the job to. Queue also has a cluster queue, which is a global queue. It's not a namespaced object, and that's really when queue can make sure that the resources required by the Ray job. So Ray job creates a Ray cluster. For those of you who are familiar with it, it creates a Ray cluster, runs the job on it, and then deletes the Ray cluster. So Q makes sure that the resources that are required by that Ray cluster, once they're available, it admits the job, and then we use DWS to work on GPU obtainability to really dynamically get access to GPUs once the workload is admitted. So this has been a great offering from GKE. We have seen users queuing their jobs a lot more often, and this really helps. It goes back to the problem that we talked about, underutilization and over-provisioning of GPUs. It really helps that problem and makes sure that the GPUs that we have, the reserved instances, we're utilizing them to the best of their capacity, and we don't have resources that we are paying for and no one's using them. So that's how it works at Spotify. Again, I'll tie two concepts, two things that we talked about. I'll try to bring the points together. From GKE side, we use a lot of optimizations. Three categories are talked about: network optimizations, storage optimizations with GCS Fuse, scheduling optimizations with Q and DWS. On the Hendrix side, on the platform side, the aim or the message we want to deliver is you really have to think about the complexity of these features, and also how do you provide that feature to the users such that they don't have to think too much about it. So we have these great features that we use, solving our problems, and we spend a lot of effort on making sure that we are lowering the complexity. So as a user, you can really focus on the workload that you have and not think about the resources and the infrastructure level struggles. All in all, it has been a very smooth experience working with GKE. We always appreciate the response time and the openness to work with us. And so yeah, this was, in a nutshell, Spotify's Hendrix platform. We talked about some quick problems, but if you are interested in other problems that we're running into, I will be here. Feel free to reach me, and happy to chat about it.
So I think we got about 2 minutes for additional questions. Hopefully more of the questions are directed to Abdullah, because he's actually building this stuff in the real world.
Hey, quick question. So you mentioned you use GCS Fuse, which is not POSIX compliant. Have you run anything to an issue when you're running against Ray, anything that's not causing problem due to the POSIX incompliance?
So just to repeat the question, so the question is about use of GCS Fuse and POSIX compliance and sort of the challenges that they've seen in terms of, yeah.
So it's a recent offering. We haven't seen too many issues with it. We actually had, so before GCS Fuse, we had an internal solution for storage, but we recently switched to GCS, so I guess it's yet to be seen if there are issues in the future. So far, teams using it, it's been a smooth experience. We don't, no issue. Are there any more questions? Hi.
So any performance issue for the Fuse? So have you ever used hyperdisk ML?
So the question is, performance issues with GCS Fuse, have we looked into?
The hyperdisk ML is a new feature.
Hyperdisk ML. We have not yet. It's still, Gen AI is a very fast evolving field, so everything happens too quickly. So far we have not, but it's something if there are issues that we see our users facing, we're open to looking into it, but we don't currently use it.
Yeah, Hyperdisk ML is a relatively new offering within GCP. So, but I'd be happy to answer any questions specific to HTML. And it's a different storage solution, obviously. In general, we see customers still gravitating towards GCS as sort of a central repository and then hydrating the data from GCS into HTML. But it's a block storage solution different than object storage. So there's some additional complexity there that you get in exchange for the performance.
I'll be taking more questions.
Any other questions?
So when you're dealing with like other teams configuring like the number of resources for jobs, you ever had your requests dealing with using a fractional number of GPUs, or do all the teams focus on using a full number of GPUs?
Right. The question is if our teams use fractional GPU or whole GPU to overcome the problem of GPU utilization. Currently, they use whole GPUs, but fractional GPU, if there's a problem in the future, is something that is on our roadmap. I think.
Any other questions? Excellent. Thank you so much.
Awesome. Thank you.